Monday's quiz has three main topics on it: gravitation, Kepler's laws, and simple harmonic motion. Also, I looked back at the unit exam, and there is a fluids free response question on it. So, reviewing fluids a little bit this weekend isn't a bad idea. It's not on the quiz, but it will be on the unit exam, one fluids free response question. Alright, quick rundown. Gravitation is referring to the universal gravitational equation, Fg equals g m1 m2 all over r squared. Kepler's law, the biggest one, is Kepler's second law, which says planet in an elliptical orbit will cover equal area in equal time. So if this area is the same as this one, the planet sweeps the distances along the arc in an equal amount of time. Simple harmonic motion for a pendulum and a spring. Dealing with a pendulum, the period of the pendulum, or the time for one oscillation, is 2 pi, square root of the length of the pendulum over gravity on the planet. And then for a spring, 2 pi times the square root of the mass on the spring over the spring constant. Alright, universal gravitation, you'd be able to use this. Fg equals g m1 m2 all over r squared. You know that equation, and that g is 6.67 times 10 to the negative 11th meters cubed over kilograms seconds. You'll be able to use this equation both with plugging in numbers, estimating order of magnitude. That's what you do with all the exponents. So if the masses are 3 times 10 to the 5th kilograms times 2 times 10 to the 2nd kilograms, you know that that's 6 times 10 to the 7th kilograms. Okay, so adding the exponents when you multiply. You did stuff like that both with me and with the substitute. You need to be able to answer questions like what happens if I double one mass, double both masses, double the radius. Be able to solve that kind of question. And also, you need to know that for planets and other objects orbiting in outer space, gravity is the centripetal force. And so if you were to try to figure out the velocity of a planet in its orbit, you might do something like Fc equals m v squared over r. You think, wait, I don't know how to figure out Fc. Well, Fc will be that gravitational force holding it in, m v squared over r. And you might be tempted to replace Fg with mg, but we're not on the surface of the Earth, we're out in space. And so instead we do g m1 m2 over r squared equals m v squared over r. I'm going to rewrite that just to talk about it a little bit. So once you've set this up, you do have to be careful because there are a couple different m's. The m here is the mass of the planet, and so it is the same mass as whichever m you chose on the left side to be the mass of the planet. So if I chose m2 to be the mass of the planet, then that would be the same as the m in the centripetal force equation. If I chose m1 to be the mass of the planet, it would be the same one over here. So you can cancel them, but you have to know which one you're canceling, the mass of the planet or the mass of the sun. And it's only going to be the mass of the planet. Or if we're dealing with like a satellite, more generally, it's the mass of the thing that is orbiting, not the thing being orbited. So if we have a satellite going around the Earth, it's the mass of the satellite, and over here one of these would be the mass of the Earth and one would be the mass of the satellite. It's the mass of the thing orbiting, the thing that's actually going in the circle. So remember, the m in the centripetal force equation is the mass of the thing going in the circle, not the mass of the thing at the center of the circle. Alright, Kepler's laws. You need to know that planets orbit in an ellipse, and that in an orbit, if you were to draw a line from the sun to the thing orbiting, as it sweeps along a certain arc, you'll always take the planet the same time to cross through the same area. So if these two areas are equal, happen at the same time. And from that you can answer, where is the planet moving faster? Well, if they go orbit in the same time, then the place with the longer arc, it has to move faster, has to go faster to get through here in the same time as it did through the other place. You can also answer questions about energies. So the further the thing is from the sun, the slower it has to be going, because it has more potential energy, so it had to lose some kinetic energy. And over here, where it's close to the sun, it has to be going fast because it has less potential energy now that it's closer to the thing it's orbiting, and therefore must have more kinetic energy. And so you need to be able to answer questions about that. Simple harmonic motion. Now you need to be able to understand things about the energies going on here, like we did that question where we spent 10 minutes, Annabelle went to the board and said what's true about the energies in different places. So you got to be able to take the time to think about energies and velocities. Remember this one on the right, the spring, involves both Hooke's law for force, spring constant times displacement is the force. So when it's at equilibrium, no force and no acceleration. And you got to remember that potential energy for a spring also depends on displacement, 1/2 k x squared. So no displacement, no potential energy, so no potential energy at equilibrium. Over here, this thing has gravitational potential energy as we go. And so the lower it is, the less potential energy it has. And therefore, the lower it is, the more kinetic energy it has. The higher it goes, the greater the magnitude of potential energy, more potential energy it has. The lower it goes, the less potential energy it has. Also, if you're determining the time, or for the period of each one, how long it takes for one to go one full oscillation there and back for this, up and back down for this one, if this is, say, our release height and we've stretched it out. The time for the pendulum is 2 pi, the square root of L over G. And I'm going to ask you questions about what would change the period of this pendulum. So notice that for the pendulum, the things that affect its period are the length of the string and the gravity of the planet it's on. So if we take this pendulum to another planet, its period will change based on the force, the acceleration of gravity on that planet. And if we change the length of the string, its period will change. Making the length of the string longer makes the period longer. Making the length of the string shorter would make the period shorter because it's in the top of the fraction. L is in the top of that fraction. Increasing gravity makes the period shorter. Decreasing gravity makes the period longer because that's in the bottom of the fraction. And if we multiply the length by 2, we change the period by a factor of a square root of 2. And that's true for any factors. So if we multiply 4, square root of 4, also known as 2. If we multiplied the gravity by square root of 2, we would change, if we multiplied the gravity by 2, we would change the period by a factor of 1 over the square root of 2. Things to keep in mind. For the pendulum, its period is 2 pi times the square root of the mass over the spring constant, k. So if we took the pendulum, if we took the spring to a different planet, we would not change its period because gravity does not affect the period. That's hard to think about because you might say, well, wouldn't it pull down more? Well, yes, but then it would also receive a greater force to restore it back. So the period doesn't change based on gravity. However, if you change the mass on the spring, that would change the period. And if you change the spring constant, the stiffness of the spring, that would change the period. So those are what affect the time it takes for that, both of these objects, the pendulum and the spring, to oscillate back and forth. And remember, if you change something under the square root, that change keeps the square root. So if we multiply the spring constant by 2, we change the period by a factor of 1, the square root of 1 over 2. And that's it. Good luck on the quiz.